Okay, so welcome to this thesis defense of Tina. So I am Agnès Desaulniers. I will be the president of this jury, and we have a very nice jury with 3 reviewers and Annie Farid, who is online, coming from Berkeley, California, William Fesch, who is professor at the University of Montpellier, Luisa Verdoliva, we will join online, who is at Naples, Coloma Ballester from Université Pompeu Fabra, Barcelona, professor. And we have also 2 industrial members, invited members from Agence France Presse, Denis Tessou and Bertrand Rouville. Thank you. And the 3 advisors, directors, Raphaël Grandpon, Jean-Michel Morel, and Miguel Colon. So, Tina, you have about 45 minutes to present your work. So please turn your cell phone up, like in the theater. And so you can present your work, and then we will have questions.
Okay, so thank you for the introduction. So hello, everyone. I'm very happy to see all of you here today, and I'm very happy to present the work I've did these past years on forgery detection. So first, I'm going to talk a bit about image forgery, of course, and I give an overview of image forensics before talking more specifically about JPEG images and so JPEG compression. And then I'm going to present the main contribution of my thesis, which is the algorithm called Zero. So you will hear this name quite often. And then another contribution, which is how to evaluate image forensic tools and also how to evaluate Zero. So first, image forgery is as old as photography. People have been forging images. Even the people who invented photography forged themselves images. So before the era of digital photography, people have been removed, faces have been smoothed. So here it's on a negative film. Someone has scratched the negative film. So this actress has a nice skin. So it's the applications of forgery, for image forgery is quite the same as today, but the difference is that now we have digital photography, and soon after the creation of the first cameras, we have Photoshop. So Photoshop arrived in the 90s, and since then, people have been doing forgery quite the same as before, but easier. It was more accessible. It was here, for example, to make the image look nicer, but also this image look nicer. But it can also have some illegal aspects, so to commit fraud or to spread fake information. So the difference now is that the images we see, we have a different relationship with all of these images. We see images everywhere. They have become an important source of communication. When you go online and you want to access the news, well, you have all of this information that has the picture next to it to use as a proof, for example. The news is also different because you have access to a lot of different news. So for the same subject, you have different sources. And even more, you have news that arrives very quickly by unverified sources, such as on social media. So for example, here, I don't know if you see, so the news is not only particularly for me, but it's also quite fast because they're already talking about this PhD defense, which started 2 minutes ago. So if we click, for example, on this information, on this news, we see that people are talking about it and they are taking pictures and spreading a lot of information. So the information goes fast. Information is with images. So we need a way to be able to verify all this information quickly and all these images. So what to do? The first reflexes people have is, well, of course, look at the image. This is the first thing everyone should do. Then something we could do is analyze the image file, because an image is often goes with some metadata. So it's the information where you can see when the picture was taken, with which camera, and sometimes even where. But this information is stripped away when you post something on social media. Something else you could do is perform reverse search. So you want to find the source of the image. So when it was posted for the first time on the internet, for example, but this doesn't work in this case. This image is not famous enough. This image, I know where it comes from because I took it. I took it last week, and I sent it to our school, which posted this image. But then people started spreading fake information and all these posts by taking this picture and applying different forgeries. So the question is, how can we verify the image just by the image itself? Because we're not supposed to have the original image as I did here. Hopefully, what we have is image forensic tools. So image forensics can be divided in two categories, the active approaches and the passive approaches. The active approaches is applying something, embedding an information in an image before sending it. So this is what I should have done with my image, but I didn't do that. So now we have to use passive approaches to detect any forgeries. So passive approaches can also be divided in three categories. We have the physical integrity, so we could assess the integrity of the image of the scene to see if all the shadows are the same through the whole image, or the illumination, or the perspective. We could also assess here on the right the semantic integrity. So here on this picture, one way of telling that this image is fake is that these two people, famous people, could not have been at the same place at the same time. Another way is digital integrity, is by analyzing the operations the image has gone through, because a digital image goes through several operations. So for the moment when the light goes through the lens on the sensor, there are several operations. So we arrive at our final image. Then this image is stored. So here I'm going to talk about JPEG compression, because that's the compression standard that is used on the internet and on social media. And if you want to look at your image again, you need to decompress it and look at it. And then if you want to tamper it, to forge it, then you do it afterwards. What's important here is that all these operations provide important clues that are exploited in image forensic. They all have an impact on the image and create some kind of signature, some kind of watermark, as we could have done for the active methods. But this is even without doing it before. The fact that the image went through all of these steps, it leaves a trace to the image. And there are lots of methods. There are lots of ways to assess all these steps. So all these steps can be assessed. You could verify, for example, that the noise through all the image is the same. You could verify if the JPEG compression is correct through all the scene. And there are lots of people for these past more than 15 years that have been working on this. They have been working on assessing the integrity of all of these steps through an image and detecting forgeries as anomalies in one of these steps. So what is a forgery? I have some examples. I showed it, maybe it's a bit too quick earlier. Now we can look at them into more details. So we have forgeries that can be what we call in-painting. So parts of the image here have been erased. These three objects, the three people, have been erased. We also have what we call copy move. So the same object has been copied several times, so it's duplication. We also have what we call splicing. So we have new objects from another image or from other images have been added to this one. So now we can use all the forensic methods I showed previously and apply them to these four images here. So these tools assess different steps of the image processing chain that I showed before. So we have methods that assess the compression. So they are all work quite well, and they enhance the area that has been forged. For example, here, some are regarding the noise level, some are regarding other steps of the processing chain. But the thing to see here is that they all give heat maps, and the area which is enhanced is where where there is the anomaly, where there is the forgery. So people use these filters quite often. I use them every day, but there are also people such as journalists and fact checkers. So there are people that spend a lot of time every day or weekly to verify an image, and they spend a lot of time doing so with all these tools. They really enjoy these tools. During a project we did with AFP news agency, a survey was conducted through some AFP fact checkers, and they said that, well, they loved these tools, but that they had too much false positive, and they were too hard to understand, and they needed interpretation. So what we did in the team is that we proposed methods that are automatic, so they don't need an interpretation, that are task-based, so we know what they do, and we try to control the false alarms, so the false detections. Some in the team who are here today worked on the different types of traces, so the CFA traces or the noise level. I focused on the JPEG traces, the JPEG artifacts. So now I'm going to go through JPEG compression. So how a JPEG compression works, because we need to understand some of the parts, some of the relevant parts. So after I can present the zero algorithm. So as I mentioned, JPEG compression is one step in the processing chain. So it's the operation which permits the image to be stored such as it doesn't take too much space in memory. And then if you want to look at your image, then you have to decompress it. So JPEG compression, first step, is to convert the image, the RGB image, into another color space. So we have the luminance, where we have most of the information, you can see here, and two chroma channels. These two chroma channels are often subsampled. But here, and during all this presentation, I'm only going to talk about the luminance channel. And when I will say image, I'm actually talking about the luminance channel of the image. So second step, but the first important step of JPEG compression is dividing the image into 8x8 blocks. And we apply to these 8x8 blocks independent processing. The processings are applying a DCT transform, then a quantization, and then storing these values. The quantization here is the step that allows the data to take less space in memory. And it depends on the quality factor, which is a value that goes from 1 to 100. The smaller this value, the smaller the file size at the end. But let me go a little bit deeper into each of these 8x8 blocks. So here is one 8x8 block. Here's the pixel values subtracted by the 128. Then we apply a DCT transform, and we get the DCT coefficients. So on the top left, we have here the mean value, here the low frequencies, and on the bottom right, we have the high frequencies, and the human eye is less sensitive to this information. So this DCT coefficient is then quantized. What it means is that the values here in this table are divided with the according value from the quantization table, and then rounded to obtain a quantized DCT coefficients. This quantization table depends on the quality factor I mentioned before. The bigger this value, the best quality, but the smaller the values in the quantization table. What it means is that, well, if you want to store, if you want to have a file that is smaller, you need to have bigger values here. So the values are more quantized. And so what we observe, and this is the important part, is that there are lots of zeros in the DCT blocks on the bottom right in the high frequencies. And then the JPEG compression algorithm exploits these long zeros and stores these values in an efficient way to get a JPEG file. So if you want to look at your image, you have to decompress it. So you have to apply these same operations, but in an inverse way. And then what you get is JPEG compressed images. What you see is with a quality factor that is quite low, we observe, well, poor quality image. Actually, what you see are blocks of size 8x8 that are caused by the division of size 8x8 we have here. And the bigger the quality, the less visible they are, but still this signature of JPEG compression is still there. Let me show it a little bit more into detail. So on the left, you have an uncompressed image. On the right, you have the same image, but compressed heavily. And you observe this, signature of the JPEG compression, which is these blocks of size 8x8. And they form through the whole image what we call the JPEG grid. So here in black, it's the JPEG grid. There are, so as I showed before, there are lots of methods that work on JPEG artifacts. They can exploit this grid I just showed you, the quality, so how much it has been compressed, or other features that are singular to the JPEG compression standard. And in my presentation, I'm going to focus on JPEG quality, JPEG grid. So JPEG grid detection, the goal is to detect this grid. So I put another example here. So in red, we have this grid that we're looking for. This can be done in several ways. I have done myself 4 different ways, but the first one being by enhancing this grid by applying a cross-difference filter, for example. The second one by analyzing the DCT coefficients. The third one by exploiting the fact that JPEG compression, its goal is to have files with a small size. And finally, by looking at the DCT zeros, and that's the algorithm I'm going to present now. So since I'm looking at the DCT zeros, you understood why the algorithm was called zero. So the zero algorithm is an automatic JPEG grid-based algorithm. And our goal is to control the false alarm, so do not have too much false detections, actually to control them, so to have 0 false detections. We see here on this example that the original image, here is the intermediate step, and at the end, we don't have any detections because the image is authentic. And on the bottom, we have the same image that has been forged. We have an intermediate step, and then we have our detection, which I hope is quite understandable and doesn't need any interpretation. So the zero algorithm has 2 steps. First, this voting maps are going to be created, and then the statistical detection, which will lead to this result. So the voting process. From now on, I'm going to define a grid. So if you look at the compressed image here, you see the grid in red. But since the blocks are of size 8 by 8, there are 64 different possibilities for a grid through an image. So I'm going to define a grid by the coordinates of its origin. So you have 8 possibilities horizontally and 8 vertically. And then I'm going to ask each pixel of my image to vote for the grid origin it belongs to. So 64 different possibilities. And here, for example, this one is correct and this one is not. To do so, I'm going to apply a DCT transform, an 8 by 8 DCT transform. I'm going to count the number of zeros in each of these different positions. And well, what do we observe? Here on an uncompressed image, we observe DCT coefficients. Okay, with some zeros. But if I do the same on a compressed image and in the correct position, then we see a lot of zeros that appear according, of course, to how much the image has been compressed. To create our first step, which is our voting map, we are going to ask each pixel to vote for the grid origin having the most zeros. So there are 64 different candidates, 64 different colors. As a convention, we created the color vote map, so it's nicer to look at. And a 65th color, which is going to be black, is when the votes don't decide, the votes are not valid in case of a tie. So what we see on an uncompressed image is that the votes are quite random. On a compressed image where the top of the image is coherent with the beginning of a grid, then we have the grid 0, 0. So from now on, green, the votes that are green correspond to the top left of the image, so 0, 0. We have the perfect block on the top left. Then if the image is less compressed, it's maybe less obvious until quality factor 99. The method works until the quality factor. Because 100, quality factor 100 is almost what we can say lossless because they don't put any values to 0. So the question is how to decide that one vote map, for example, here globally, voted for a grid or no. So we have to, what we want to do is we want to see if one vote is significant or not, because even if we take the most voted grid, we're not sure that it is by chance or if it's really a significant detection. So what we do is that we use a validation step. So here, 2 examples, uncompressed on the left and compressed on the right, the same as before. And given this window, we want to know if a vote for a particular grid, the vote 0, 0, is significant or not. Here we see on the left that there are almost 5% of the votes who voted for this grid, on the right 9, but both are more than 1/64, so more than random, but still we need a way to decide. We need a way to have a detection threshold, and to do so, we use the a contrario validation theory. So the a contrario validation theory, we need 3 ingredients to be able to use it. First, a background model, where you should have no detections. Then a family of tests, what are we going to test? And then which are the observations to test? So in an uncompressed image, or even more on a Gaussian noise image, if we apply this vote map, we compute this vote map, so we apply the DCTs and compute the vote map, we shouldn't have any votes that are chosen one rather than the other. So it's uniformly distributed among the 64 possibilities. However, what we observe is a correlation. Here we observe that there are blocks of size 8 by 8 because the votes are correlated at distance 8, because they share the same DCT blocks of size 8 by 8 that we computed to get this vote map. So what we do is that we decide to take the votes at distance larger than 8, which are independently distributed. Then we need a family of tests. So all the windows in the image can qualify as a family of tests. Of course, there are 64 possibilities for each of these windows, so 64 times the number here, because we take candidates at 8 of difference. And then we have also 64 different candidates, so we multiply this again by 64. So this is the number of tests we can perform in an image. Now we need to compute the probability of obtaining the votes under our background model. So we have k votes for among the n votes, and we compute here this probability. And when this is small enough, we can say that we can reject the background model and declare that this is not by chance. These votes are significant for a certain grid origin. So now that we have our 3 ingredients, we can follow the methodology and define a number of false alarms. And so for a certain grid and a certain window in the image, we can define here the number of false alarms, which is number of tests times this probability. And we compute this for all the candidates. And we say that a candidate has been selected when at least one of them is smaller than a certain threshold. And we can compute this for all of the different grids. So let's get back to the example, maybe easier to explain here. So there are n votes in total here on for the 2 squares of the image. Here 30 voted for this grid, and here 56. So if we compute the NFA, what we obtain is a very big value and very small value. We decide to put epsilon to 1 as a convention, and we see that it's very bigger than 1 and very smaller here. So in this case, no JPEG grid has been detected because the most voted grid was not significant, and so the others neither. And on this side, we only have 1 grid that voted significantly. So for the JPEG grid origin 0, 0, the top left of the image. And that's actually the result we get here. So here we have no compression. Here we have a JPEG grid 0, 0, and up until the quality factor 99. If we apply this so globally to the image here, we can directly have one application, which is detecting crops after JPEG compression. So we have 63/64 chances to detect a crop that has happened after a compression, because the global grid is not aligned with the top left of the image. So here. But now we ask ourselves, how can we apply this to detect forgeries? Because forgeries are local manipulation in the image. So here I put a vote map without showing you the forged image. So the global grid voted for the 0, 0. So it's called this the main grid. And now locally, I think you see that there are votes that voted for something else. We see other colors locally in the image. So this is actually this kind of forgery here, local shift, but we will see then. So what we do now is that we go through the image and we partition it into the groups of pixels that voted for something else than 0, 0, so something else than the main grid. Then we create bounding boxes around these regions, and we apply the a contrario validation I presented before. If the detection is significant, if the NFA is small enough so that it doesn't happen by chance, Then we compute a forgery map here. And that's how we detect foreign grids. So locally, we have grids that have been shifted. And this happens for example, copy moves, internal copy moves here. The grid has been, this part, I'm going to show here. This part here has been copy moved several times, and we detect it here. Here is another vote map. A little bit more complex to understand. The whole grid voted for 0, 0, so that's the same. But locally, we observe an anomaly, but it's not as clear as before. It's not one other color. It looks like having a lot of random votes. And if you remember, it's like applying the voting process to an uncompressed image. So it's like having here maybe missing grid. But how can we be sure that it's because of that or just because of the image itself? So what we do is that we apply a second compression to the image. We simulate, we induce ourselves a compression, very slight, so quality factor 99. So we can see if this area which is missing a grid will get the grid that we induced. And then we create a new vote map. So the view vote map is the vote map of this compressed image, but we have discarded the votes that voted already correctly for the main grid 0, 0. And then we do the same. We partition the image into group connected pixels, which voted for the grid we induced. And we create bounding boxes to apply the a contrario validation and have our forgery map. So in this case, we have detected what we call local missing grids. For example, here we had a missing grid because someone wanted to commit insurance fraud and erase this part from my mom's car. So this is the result. So to sum up the 0 method, first we have an image. We compute this vote map on this image. We get the result globally. So we apply, we want to know what are the global grids. If there are none, then the image has not globally compressed. If there are several, we'll see this case soon. Here, for example, we have one global grid. The image has been compressed. Then we look into the image for areas that have a grid that is different from this one to get our foreign grid mask. We compute this simulated version of our image, this new vote map, and we have here the areas that have a missing grid, so that don't have any traces of this global grid here. And then we merge these two results. So we have our two binary masks here. In the red, we have the foreign grid, and in blue, the missing grid. So let's apply 0 to some images from famous data sets. Here, for image, the result is here. The image is JPEG compressed globally, and locally we have a foreign grid. Here, the image is compressed globally, but locally we have a missing grid, here in blue. Here, the whole image was not compressed, comes from an uncompressed data set, but the forgery, so the splicing coming from another image, comes from an image that was JPEG compressed. So here we detect a grid, not a foreign grid, the only grid. So this is when the image has not been recompressed. The examples I showed you for the data sets are images that have been downloaded, tampered, and then saved in a PNG format, for example. So what happens in a real life, in a real case scenario when the images are compressed again because sent on the internet? Well, we can take our examples from before. So we have our original image, our copy move, our in-painting, and our splicing. And we can apply 0 to these images. So we have the vote maps, whole grid 0, 0, no false detections here. We have here a whole grid 0, 0. It's less obvious than the examples I showed because locally the vote map has both the traces of the second and the first one. But still we have foreign grids here. Here the splicing, we detect missing grids. So what has been added from another image, even if it was a compressed image, has lost its traces and has been put here, and we detect missing grid. So they have the JPEG compression of the second compression, but the first one was stronger, so it overcome the second one. And here we have, so in painting, so even by looking at the vote map, you can see that in painting is actually a bunch of copy moves, small copy moves in the image with different colors. And so we detect them as foreign grids. Oh, here is an example of so the same thing, tampering, but before sending the image again on the internet, we're going to crop it. So this is an image I just did. No, this is one of my images. One I forgery I can control, so I'm going to show you maybe into more detail. So this image, well, I'm not going to tell you what I did. I'm going to show you the vote maps, and maybe you're able to understand since the method is quite explainable. So we apply the method globally. We get 2 global grids. This corresponds to the fact that there was a compression here. The image was cropped, and then the second compression, which is not aligned. Then the main grid, so the strongest for compression between the two, was the first one, because it's the main grid, most voted one. We get our vote map, which is so blue, not green, because the image has been cropped. And inside of this, we get, so here, if we look at the detection result, we have some, well, here it's easier to see, some splicing. For 5 objects have been spliced. Here we have a copy move. Sorry. Here it has been erased and has been moved here. So it's a copy move and an in painting. And we detect almost all of them. Here the missing, here should be maybe missing an area. Well, it has been overcome by the second compression. So it's 4 in grid here. But here we're missing someone. We're missing one detection. So this is an interesting case because it shows the limitations of the method. The limitations being that, as I mentioned before, there are pixels that voted black, which means that they didn't vote, we didn't take into account their votes, for example, in case of a tie. And that's what happens in saturated areas. So we don't take into account these votes. And also when the forgery is too small, not too small regarding the image, but regarding the bounding box we chose around it, then the detection may fail, not too significant enough. So now, as I said, this is my picture, so I can show you what I did a bit. I can see the robustness of this second compression to this image. So at first, when I exported it with my software, I chose a high-level quality. This actually means compression 100. And JPEG 0 doesn't detect the compression at 100 because it doesn't put any values to 0. So it's quite the same as having a PNG format for the algorithm 0 only. So what I see here is I detect everything. Well, except here, I don't know why we don't detect this object again. Then if I apply a stronger compression, this is what we got on Twitter, but here I did it on purpose. Well, we have our detections here. We have 2 grids, but the main one is the first one. We see that the detections were missing grid are not so robust. Here the compression was maybe a bit harder. So the blue is less robust and less reliable than red. If we apply a even stronger compression, so the second one being just a bit stronger than the first one, then what we get is, once again, 2 compressions. When the image has been cropped, we see it because the grids are not aligned. And the main one becomes the second compression. So it overcomes the first compression. We see here the vote map mainly has the green color. And what we get is a map, a detection map, but inverted. And of course, if we compressed, the second compression is quite harder, stronger, then we don't detect anything. It has completely overcome the first compression. So as all forensic methods we all have counter forensic methods. We all have limitations, and strongly compressing the image again is one of this one, but it's also one of a lot of other methods. We also have other kinds of limitations. For example, resampling. If you resample, so if you downsize or if you rotate your image, then there are no longer these JPEG artifacts of size 8 by 8. So the detection is there are no JPEG grids. So we have no false detections, but we don't have any detections. And other natural limitations this time is, well, if we perform a copy move, so this area here has been copied and moved twice, then we don't, then if it falls in the correct position, so we have 1 chance over 64 that it happens, then we don't detect it. So here once it fell in the correct position, but not the second time. But what we can detect are maybe the borders if they have been blurred, so they fit perfectly in the image. And of course, this limitation, it does not work on uncompressed images and images that have never gone through compression. but still no false detections, and it says that there are no JPEG traces in the image. So now I showed several experiments on 0, but there is a way that we could evaluate more thoroughly this, and this is another contribution of my thesis. So it started by trying to evaluate all methods. So what we do usually is that we look for forgery data sets and we apply the methods on these data sets. But when they are made manually, so when the forgeries are made manually, well, the size of the data set is quite small, so we don't have so much examples. And if they are made automatically, then they may seem unrealistic, and they have strong edges, so they can be detected by other reasons than what we are really testing. So what we propose to do, so this is the work I did with 2 of my colleagues that work on other traces, as I mentioned, the CFA traces and the noise traces, is that we propose the methodology to create forgeries without the forgery itself. So what we want to do is to add the traces of a forgery, but not the semantically the forgery. And the goal is to evaluate existing methods and so the existing trace-based methods, but also all the methods to see which trace they are sensitive to. So how we did that, we started with a raw image, to which we applied 2 different processing pipelines. Then we have a mask, and we merged these 2 images to get a forged image, which is semantically the same as the input image. But it has locally a different processing pipeline than globally. And we have the control over all of this processing chain, so we can only change 1 parameter in one. So we can really test the difference of 1 trace. So what we did with my colleagues is that we did some for CFA artifacts, some for the noise level, and some for evaluating JPEG traces, and even more JPEG grid. So that's what we are going to see. The JPEG grid. So we have 2 processing pipelines which are exactly the same up until the JPEG compression with the same quality. But what differs is the grid origin of the image. So when we merge these 2, we get a forged image because locally there is a shift in the grid, and globally it's the correct grid. And here I applied the 0 on this trace database. So we have, of course, good results up until 80%. We have results that are not perfect, but still okay because of the compression level, which is very high. As I said before, when it's 100, we don't detect anything, no JPEG grid. And we have the same limitations I presented before, the saturated area and the small forgery. I don't know if you see it here, very small forgery, very small. So it's also useful to apply to all the methods from the state of the art to see how sensitive each forensic tool is to these different traces. And the goal in this is to see how we can combine them. Here we see that okay, it's good, the CFA traces are sensitive to CFA, but when the image is compressed again here, then it doesn't work. We see that some methods are sensitive when several of these traces have changed or inconsistent, and that's the detection here. So for example, it's an example of how useful it is to have several methods. We're not going to be able to detect all the forgeries with only one, is to have all of these methods of different families next to each other. For example, here it was the image that was not compressed, so no detection. So here I applied the algorithms of my colleagues who who work on the demosaicing traces. So no JPEG compression is a good thing for applying this method. Here is noise, but also on specific types of forgery. So here copy move, we have specific tools. So now that I presented an overview of all of the methods, I hope that you have new reflexes. So look at the image, analyze the image file, but also use forensic tools. And you can do so by downloading, it's no advertisement, but you can use the tool by the Agence France Presse, where inside what we did is we divided these families of tools by the different categories, the traces they impact. And also, I'm very proud to say that we added 0 to this tool, which is used worldwide by fact checkers and anyone. You can all download it. Voilà. So just to finish, I wanted to give a summary of my contributions. So I worked mainly on JPEG artifacts. Here are two parts I didn't mention during this presentation is the improvements of state-of-the-art methods that where I added statistical validation, the a contrario validation to them. I also worked on new methods to reverse engineer an image because it's useful to just know if an image has undergone, has went through compression and which quality, which quantization table. And here are the two I talked about during these past 40 minutes, the zero algorithm and the trace database that was teamwork. So for future lines of research, I would like to adapt these methods to the luminance channel, so the chroma channel, sorry, because as I said at the beginning, we only talked about the luminance channel. Also to work on the robustness of this missing grid, the blue part in the zero algorithm. I would like to create, because the bases are here, but to create a new automatic JPEG quality-based detection method. So we have the JPEG grid, but maybe JPEG quality. We would like, as a team, to add post-processing operations to the data sets we have in the trace methodology, and also new data sets. And in the long term, I would like to investigate a bit about the new compression algorithms that exist, especially for images, and to work on these new fake images. So image forgery is not a recent concept, but there are newer tools to do so. So with diffusion models. So I'm just going to take 1 minute to talk about this because I find this quite interesting. Here, I forged this image by using diffusion models, a stable diffusion. So what I did is I gave this image that you now well know. I added this mask and I asked the method to put a student in the classroom here, to put Taylor Swift here, to put, well, classroom, it means I wanted to erase this object here, and of course, to add Santa Claus behind the laptop. And that's what it did. And what we see is that even if it was able to reconstruct the chair in the room, the chairs you're sitting on, it was not able to reconstruct the JPEG grid, because here we see in the vote map that the grid is missing. We have a missing grid here, so it can be detected. So I would love to work on this. So I just wanted to show you this to see how exciting and interesting it is to work on image forgery, on image processing. Everyone understands it when you talk about it. It's so interesting that I had the chance these past years to not only work, write papers, go at conferences, have my code published and used, but also work in different projects with some of you here. And also teach a class to journalists and who use these tools, so image forgery tools, and during science fairs, and create some popular science content. So it was quite a journey. And I'm very happy I did this with a great team and my family and the colleagues and everyone was here actually, but I didn't take the picture of today. Stable Diffusion was not able to create this image. So thank you all, and I am looking forward for your questions. Thank you.